Hello, my name is Michael Machiraju, and this is Lab 4, Oscillations. In this lab, this is the introduction. The purpose of this lab is to determine how well the fundamental principles of Newton's second law and the energy principle predict the motion and energy of changes of an oscillating mass on a spring. It appears that there were random errors during the experiment. However, Newton's second law and the energy principle can still be used to accurately predict oscillating systems. Other principles used in this lab include Hooke's law, kinetic and spring energies, and gravitational potential energy. So here are the major physics concepts. You have Newton's second law, which is F equals ma, and the energy principle, which is delta E equals the work external. So that just means that any work done on the system is added up, and that is equal to the change in energy. This is the experimental design. So the system is defined as the spring, mass, and the earth. The initial conditions are a position of, and this is a vector, so the x position is negative 0.863, the y position being 170.1, and there is no z position, and that's in meters. Velocity is 0 meters per second, and the mass is 0.402 kilograms. As you can see, this is the spring, and this is the little mass at the end of the spring, and this is the tracker software. So now we get into the actual code of the experiment. So here are the constants and energies. So this is some of the constants right here, and then this is how the energies were or right here, this is how the energies were calculated. This is kinetic energy, gravitational potential energy, and then the spring potential energy, and then of course this is the total energy. This is the calculation loop. Here are the initial energies, and on this one, we calculate the gravitational force. On this line, we're calculating the spring force on the mass by the spring, and then here we add both forces together to create the net force. Here we're applying the momentum principle. That's where Newton's second law comes in, as mentioned earlier. And then of course we're updating the spring position here. This is the calculation loop continued. So these are the energy changes. So that's delta E. And then we had a rate of 200. So the results. So right when you see here, this is the experimental data. As you can see, it's very similar to a sine or cosine wave. The top graph consists of the x values, and the bottom graph consists of the y values. So based on what we did here, we used the code to create a model, and then we used the tracker software as our experimental data. And the experimental data does not perfectly align with the model that was produced by the code. This is likely due to systematic and random errors mostly. We had a systematic error in the fact that we did not include drag in our calculations in the model. And of course, in real life, you would have some air resistance, the mass would. And that's a force we did not account for. Alright, and then this is the ending questions. So we actually have two what does it mean questions. The first is the energy principle satisfied. Justify your answer by discussing briefly your plots of energy changes. According to the energy principle, delta E is equal to 0. This is because in our choices system, there's no external work because in our system we chose the spring, the mass, and the earth. And the second what does it mean question, the assignment was to find the oscillation periods based off the x and y coordinate values. So the x coordinate data, we found that it was 1.43 seconds, and the y coordinate data, I found that it was 1.59 seconds. The disparities between the two periods is because the x and y coordinates operate independently from each other.